And start.
Hello and welcome to thru.
Hello and welcome back to Calculus 2, section 6.9, Exponential Models. So if you have taken pre-calculus, you had to have a section somewhere where you learned about exponential functions, you learned about applications of exponential functions, and you dealt with the exponential growth and decay, growth of population, or decay of matter in terms of garbage or decay or carbon, C14 for carbon dating, or nuclear decay or whatever. So we have technically two types of problems that we worry about. One is related to the growth. The growth of using exponential model would be you start with some amount, call it A, and then it exponentially grows in time. And if this is y and t, the growth equation would be that y is equal to a e to the rt, where r is positive because it's exponential growth. Now we also have decay problems. Decay problem would be a problem which starts with some amount and then over time it decays. Now you have to actually wait to infinity for this one to decay. So decay would be a e to the negative rt. So this r is less than 0, right? Actually, no, r is bigger than 0 if I'm going to put negative in the formula. I'm just not going to put this condition here. There we go. So that way we don't have the problem. So this is our decay problem. And when you try to, deal with this, here you would say population growth. Now, for population growth, you can technically talk either about people or rabbits or bacteria. It doesn't matter, right? It's population growth. Or you can think about spread of the virus. Or you can think about money, right? So there are all of these different things where you see a growth as the outcome. Now on the other side, let me just divide these two. On the other side, we'll have garbage decay, radioactive decay, and then, let's say, carbon dating. And you know what I'm going to add? I'm going to add charging and discharging capacitors right in each one of these. So charge, capacitor, discharge, capacitor. So that we can actually observe all of these different areas of human endeavor, and we see that pretty much everything we do is covered by exponential functions. So you're talking about population growth and looking at the species, whatever it is. You're talking about biology. If you're looking at and there is also a lot of medical stuff that you can deal with that. The spread of the virus, again, that will be, again, related to medical field and medical research. Money, that's all going to be economics and so on. Charge a capacitor, that's going to be engineering, right? You have electrical engineering in there. On the other side, garbage decay, radioactive decay, that's both environmental issues. And then you have your carbon dating, that would be something like history and then archaeology to figure out, when you find something that is of organic origin, you can find out how old it is. And then discharge of the capacitor also goes with the charge of the capacitor, which is going to be electrical engineering. So you see that all walks of life are pretty much represented. It's just these few. I only have 8 different applications. Now there is much more of this. We can pinpoint particular problems in physics, in chemistry, in biology, and then go on with other sciences as well to find even more of these applications. Well, let's do some of the interesting things. it's interesting to state, at least for me, that within my lifetime so far, population of the planet doubled, right? It is interesting to observe and see what is exponential growth. I mean, I've been around for 39 years now, right? And the planet doubled its population within my lifespan, doubled the population. So when you think about that, you say, "Wow, that's really something." If you are looking at so let's say you are looking at these. Let's just take a look and appreciate the exponential growth. So if you have a linear growth, right, then linear growth gives us this linear increase, right, the steady increase. Exponential growth is kind of harder to picture because we don't generally deal with exponential growth on a regular day-to-day basis, even though it drives pretty much everything we see and touch. So let's think about this. Let's put a jar over here, some jar, right? That's a jar. And you put a single bacteria on the bottom, and you say that's going to be at, let's say, midnight. And at noon, which is 12 hours, at noon, it's going to be full. So the bacteria multiplies in such a way that it will be full at noon. Now, the important thing is to say that it splits every minute. So bacteria don't multiply like people or rabbits. They just split in half, and now you have two, right? So you just wait, and it splits in half, and you have two. So that's what it is. So now let's take a look at this. So at what time? So you put one of these at midnight on the bottom of the jar. At what time do you have, and at noon it will be full. So it will take 12 hours to fill the entire jar. At what time is the half of the jar full?
11 hours, 59 minutes.
Yes. So at 11:59, you have half of the jar full. So, yeah, because the 1 minute that remains, that 1 minute, every bacteria on the bottom half will split in half, and it will just fill the entire thing. Now, let's say you find a second jar, and you put it out there. At what time is this jar full?
Depends on if you have noon and midnight, you'll have that for a second.
Yeah. So, but what time is this one full? Yeah. 12:01. Full at 12:01 afternoon, because each bacteria from the first one splits in half, and all of those just populate the second one, right? Now exponential growth. If each one from the first bottle splits again, and each one from the second jar splits again, then you need two more jars. You see that figuring out the extra planet for us is not actually fixing the problem, right? Because that's the issue, right? The issue of exponential growth is that it's really fast. So now that you understand that, let's take a look at some numbers. So I'm going to use the world clock, which shows the, sorry, not the world clock, population clock. So population clock, and population clock tells us that the world population at this moment, so world population at this moment is 7,486,405, and then I'll just put 500, because by the time I finish writing 500, it will be at 500. It's now at 380. So now what I have is the world population count. Now, obviously, this is constantly increasing, so I'm just going to call this 7.5 billion because it rounds to that. Then I'm going to jump Google and take a look at world population in which year? Well, it's too close.
1944.
1940, that's the Second World War ended.
1840.
I'll pick the year. 1980. You guys are unreliable. So in 1980, so this is 2018. In 1980, population was 4.5 billion.
198. Look at that big difference.
So, well, thank you very much.
No problem.
Now, let's say that we would like to approximate the population in a year 2050. So, in a situation like this, we just use the pre-calculus solution, and then once we have the exponential model, we're going to apply some calculus and see some cool things. So let's say you have your world population at this. So what do we have? We have 2 points in time, and I'm going to call 1980 time equal to 0. So if 1980 is time equal to 0, t equals 0, then this time over here is going to be very good. And this time over here is nice. All right, good. So if I scale the time, because I really don't want to drag, these thousands through the calculation for no reason, I'm going to set 1980 as the beginning of time, right? And we are going to say that the initial population on the planet is 4.5 billion. So now we are going to use our population is equal to initial population e to the RT. Now R, in this case, is the rate of population increase. That's what the R is. All right, so now we know that initial population is 4.5 billion. We have e to the RT. And now we can use the point 38.7.5, which is today's state, to calculate R. So population is 7.5, which is equal to 4.5 e to the 38R. And this calculation will give us the R value. So we start by, hold on. What?
Oh, pretty good.
Yeah, of course. It's a serious technology. So 7.5 divided by 4.5 is equal to 1.67. It's equal to e to the 38R. We're going to ln both sides, and we're going to get now the ln of the previous answer. So I have 0.5. We need 4 decimals on these calculations because the error piles up. 38R. And R is equal to our number divided by 38. 0.0. And now 4 significant figures. So 1344. Here we have our exponential model for population with numbers that we have. So population is going to be 4.5, and that's population. Let me put population at any time. So population in terms of time is 4.5 e to the 0.01344 t. This is our population model. And now that I have this population model, I can go forward or backwards in time. And we are going to plug in 70, right? Because this population model is measuring from 1980. We want to know what is the population of the planet in 2050, right? So if I want 2050, 2050 is away from 1980, 70 years. So we're going to say in 2050, we'll have t is 70. So we will calculate p of 70, which is 4.5 e to the 0.1344 times 70 gives us 11.5 billion. So if is the exponential growth that it's given between 4.5, right, which is in 1980, and today, if we use those points to come up with the exponential model, this model predicts that we are going to have 11.5 billion people. Now, this is not actually a good model. It's good locally, right? We can figure out certain things that are, it's good approximation, but it's not a best model because we can now take a look at what this model is like when we use calculus. For instance, let's let the time go to infinity and see how many people we're going to have. If you let clock tick forever, this model will say we want to have infinite many people. Can we have infinite many people on this planet? No, we can't, because the planet has finite resources and people like to compete for those resources, right? So we can't have infinite amount of population. But if you try limit t goes to infinity of our model 4.5 e to the 0.01344 t, the answer would be infinity, which is not possible. So this model is not that great. There are better models for the population model, and one of those better models is the logistics model. Logistics model gives you an opportunity to put in what we call, to put the cap on the population, right, which is called carrying capacity. There we go. Carrying capacity of the planet is the maximum amount of people that the planet can support in terms of its resources. The land is finite and actually is diminishing. So the oceans are getting higher, swallowing the land, right, because of the global warming, and also the deserts are spreading. All of the deserts are spreading all the time because all it needs is some wind to spread the sand outwards, right, covering the soil that we can grow the food on. So if the deserts are constantly spreading and getting bigger, and the ocean is trying to drown all, there is less and less surface on which we can build and food. Now, obviously, we can build on water and live on water and then just have the land for food. But again, it's a finite resource. So at one point in time, even if all of the real estate is above water and you have all of the available land growing food, still it's going to be limited to the point of what the surface area is for that food to grow. So we see that this model of infinite population is not good. Now, if you take a look at logistics model, however, so better model, the better model is something that would look like this. You start with some kind of initial population P0, and then it goes and it flattens out. So let's say we have carrying capacity there, and there we go. So in time, This is what happens with the population in a real scale. So you have the carrying capacity K, right? And the carrying capacity K would be the limit of what you can hit. So now if you have a logistics model and you take the limit of the logistics model, you will actually come up with the number that it's the one. Now the carrying capacity has been a lot of scientific debate of where that is, because obviously it depends on which way you compute the carrying capacity of the planet. Some of the planets' carrying capacities are like low tens, like 10.2 billion, and some are as high as 15.5, or I think I heard at one point even 17 billion. But all of those numbers, as you can see, when you double the population in 50 years, right? Exponential growth. So what do we have? Another 60, 70 years till we reach pretty much any carrying capacity that is assigned. Carrying capacity means all of the planet's resources are already utilized, right? So there's no more. And then if you're trying to add more people, then obviously the issue with gathering resources will be very important. So the problem of population is there, right? It's already there. You can see that, but from some calculations that we can easily do in this class. So a better model is the logistics model. Now, going back to the problem, we are given the model that population at any time is 4.5 e to the 0.01344 t, right? That's our exponential model. What I can do is I can differentiate this and figure out what is the amount of people added, and then we can change the time to see at what time. Because remember, the derivative is the instantaneous change. So I can see how many people, right? And since time over here is measured discretely in years, right? I mean, you can put 0.5 for half a year, that's fine. But generally, we think of the time unit over here as the discrete. So you would use year 1, year 2, year 3, year 4, and really not worry about year 5.6 and 5.7. And so we can actually see year by year how many people are added each year. So I want to know how many people will be added to the population this year, because this is 2018. So I'm going to differentiate this and compute this at 38. So first, we need to find the derivative, because we need to compute in the derivative to see. Remember that derivatives are calculating the change. So I'm going to calculate the change for t equals 38, and that will give me the amount of people added or subtracted. If the number is positive, that means we added that many people. If the number is negative, that means we deleted that many people from social media. So, no, physical distance first. So what you do is you take the derivative, so we copy the constant 4.5, then we have the chain rule from the exponent, gives us this, and then e to the 0.0001344 t. So when I differentiate the exponential function, it stays unchanged, but then I have the derivative of the exponent and this one. So now I have my population in time. And population in time, we have to multiply these numbers, and we'll keep again one decimal place. So for exponents, I do keep 2. So 4 significant fingers. 4.5 times 0.01344 is going to be 0.06 e to the 0.01344 t. So this is the equation now. And I'll just say over here, calculates the change in any year. Obviously, if the number comes out positive, you are adding that many people per year. If the number comes out negative, you are subtracting that many people per year from the total that is present at that time. So this is not going to give us at all how many people we have at the time. You have to run the other calculation for that. This calculation will only tell us how many new people we have, I mean the net, born minus the dead. Actually, let me just real quick show the population website. So you see, so if you type in the world population, this will be the first hit, hopefully, right? You have the US population, and you have the world population, and you have the counter going. And now you also have the one birth every 8 seconds, one death every 12 seconds. So you see that the difference between birth and death, right, is going to be creating that type of the increase over there. One international migrant net every 29 seconds, net gain of net gain of one person every 12 seconds. And then you have the most populous countries in the world, the top 10, China, India, United States, Indonesia, Brazil, Pakistan, Nigeria, Bangladesh, Russia, and Japan. Japan, with these all tiny islands, is actually making the top 10 list. So figure it out.
It's per square mile, though.
What?
Is it per square mile?
No, this is actually total population. China has almost 1 point. So that's, yeah. Per square mile, yeah, Japan is taking first 80 spots, yes, and then the other countries. If you go per square mile because of the tiny islands, yeah.
Can you look up how many people there are?
That's what you're interested in. You gotta talk to Robin.
Yeah, he would have that information, but he's not with us today. Yeah, but you can figure out, well, how many people die. There's one person dying every 12 seconds, so multiply. Right?
One person dying for every 1.5.
Since we started talking about this website, already 5 people died, because we've been talking about a minute. All right, so there. Yeah, with him not being here, so yeah, he's contributing to the. Anyway, so that's our population clock. So now let's go back to the problem. I want to see now how many new people we added in how many people we are going to add in 2018, right? So that's going to be all of the people who were born minus all the dead people. So this is just right what we are adding to the already existent at the New Year's, right? From New Year's to New Year's, yes.
What about the aliens?
What about the aliens? So far, nothing. But let me know if they. Who is they? Oh, okay.
When they come up to the side and take them away. I don't think they can do that.
Get out.
They do whatever they want.
I heard that.
Did you get offended?
No, I got furious. There's a difference. Okay, 0.06 times E, and then 0.1344 times 38 is going to be, on this calculator here, 0.9999, and then 89 and so on. So was that 3989, 3989, and then some 432s and so on. So we're just going to call this 0.01 billion. If the calculations went right.
Wouldn't it be 0.1?
Yeah, 0.1, sorry. 100,000.
Yeah.
Sorry, yeah, right. That's 100 million. So we are adding 100 million in 2018. Right?
It doesn't seem like
100 million, yes. 1.1 of a billion is 100 million. Right? So we will be adding 100 million. So I'm going to actually now point there and say we will add 100. So 100 million in 2018. That's births minus deaths, right? So yeah, that's that. Okay. We can also figure out how many people are alive between 2 points in time if you integrate, and all of those calculations generally, we don't run, but you could if you want to. So to figure out how many people are alive from years, I don't know, 2012 to 2014, you would have to use integral, and those would be your limits. I mean, converted into the years that we have.
This function started in 1980, or?
Yeah, well, we started in 1980, but you can start at any year, and your numbers are going to be different if you pick different. I mean, we're going to be close, but they're not going to be. And again, this is not a good model that will tolerate some really large intervals of time, because you've seen it when you take the limit that it's unreliable, right? So for this particular model, you can pick different points in time and see the way it changes, but it's not going to change numbers a lot. All right, so that's the population growth. Now, what you can do, you can replace people with rabbits. You can replace rabbits with bacteria. You can talk about any one of these combinations. It's fine. Generally speaking, you are looking into so exponential model, and then you figure out the initial population, and then also the rate of growth, R. And then once you have all of that done, you will have the model. With that model, you can take limit to see if the model is viable, because you do not want population to go. Just like when you're charging a battery, you cannot have the battery charged to infinite charge. I mean, that's past certain point when it stores too much energy, the battery actually explodes and could cause a fire. So we all know the cell phones, right, that do that.
Those phones didn't explode? Apple phones don't explode.
No, but they're garbage, so that's, yeah, whatever. So they do if you give it to me. So that's the stuff. So now we have we want to create. So you're thinking about electrical engineering, right? You're figuring out the new battery type that will maybe hold more charge. So anytime you run the equations, you may need to make sure with the limit that the charge is not going to infinity, because with charge going to infinity, current goes to infinity, temperature goes to infinity. So all of these things grow together. So that was the problem on exponential growth, and we really don't care what is there. It could be money, right? The money also grows in the account. We have that the amount you get is the principal e to the RT, and this is the largest growth that you are experiencing. We call this continuous compounding, and this is the largest growth. If you ever need to take a loan and see continuous compounding, run, right? That is the largest possible growth that you can have for the interest as you are looking for loans. So continuous compounding, not good. But you know what? Continuous compounding is good if you are trying to figure out something real quick, and you know that you are actually computing the worst case scenario using the continuous compounding. For instance, you want to buy a $20,000 car, right? Now, if you ignore everything, you just know it's $20K, you need to finance $20K. I don't care if there was a a negotiation before or after, if there is a down payment to go. So none of that stuff. Let's say when everything is said and done, the amount that you need to finance is $20K, right? You can quickly figure out the upper bound on your monthly payment by running the continuous compounding formula, and you can actually find much better answer if you use the compounding. But let's take a look first at this one. So the amount you owe, right? That's the amount you owe, is going to be the amount of money you borrow times E, and then they tell you which percent you're borrowing at. So let's say you have a good credit score, and so once you're borrowing, let's say at 2.5% for 5 years, right? So if you're borrowing $20K at 2.5% for 5 years, then this E is 0.025, and then that gets multiplied by 5 because of your 5-year commitment to pay off. So that's going to be 20,000, and then you have times E to the, and when you multiply here, you get 0.125, right? So now take your abacus and figure out this value. So that's 20K times E raised to the 0.125 for a total of 22,662.97 cents. So as you can see, your interest that you are paying for the service is $2,662. So you have to pay back the 20K you borrowed, and you also give the interest. Now interest, a lot of people are, you know, in all of their ignorance, I guess, say, oh, interest is a bad thing. No. Interest is actually a good thing, which allows you to have things that you actually can't afford. If there was no interest as a concept, vast majority of the people would not have cars and houses and stuff like that. So the interest is simply the charge for the service when someone lends you money, whether that's a bank or a private person, right? So when you go to mechanic, you pay for parts and service. When you go and rent a room in a hotel, you are paying for service, right, and rent. So what is the interest? Interest is just that payment for the service, right? When you go to the bank, they are not fixing your car and changing your oil and stuff. They actually provide your service. Here is 20K, right? And then you have 5 years to return that in small installments. And by the way, because we are willing to risk to lend you 20K, your payment for the service, right? So it's different than a tip, right? Banks wouldn't be making that much money if the tip was voluntary. Like when you go to a restaurant and you have one person leave like $25 and another person leaves $5, right, for the same service on the same server. So the interest rate has actually its rules, and the rules are as you can see. So now, if you want to figure out the monthly payment, you take what you owe back, and since it's 5 years. Then it's going to be 5 times 12 months because you're paying monthly. So this number needs to divide by 60, and for 60 payments. So when you divide this by 60, you get that your monthly payment is $377.72. So you will be paying off this car loan, right, at most. Because remember, I used the continuous compounding. Generally, continuous compounding is not used, so you have the monthly payment to be about $380. So you know now that it can't be worse than that. So if any value, then if this value fits in your budget to buy the new car, well, you can buy that car where you have to borrow 20K. Now, the next model is also exponential model, but it doesn't use E. The formulas that are actually used, 1 plus R over N to the NT, where N is the number of compounds, but we keep N at 12 because you are paying monthly. So N is equal to 12. And then you still have the A to be the amount you owe, P is the principal, the amount you borrow, R is the 2.5% our rate of for the interest, and then you have time for the 5 years. So now you can plug all of these values and calculate exact. Now it's not going to be exact, guys, because if you are paying, if you see a car that is $20K, right, you have to immediately add $1,400 on top of that for the tax, sales tax. So there is $1,500 tax on $20K, right? And then there are all other miscellaneous fees over there, the title and the insurance for 2 weeks and registration and all of these other things to try. And then they have that window scratchy. That's the latest scam that they're running with the security. Right? If anyone steals your car, they can find it, buy it. So a thing that you can get on your own for like $7, they charge like $2.50 or whatever. Yeah. So, but anyway, so the idea is, but anyway, when you have all of those extra fees on the side, they all add into the price that you are paying at that moment. So, if the car is $20K, right, the window sticker, you are probably going like $25, $26K out when you are buying it, and then you have to finance whatever your down payment is not covering, the rest of it, right? So now the amount over here, so this is better price, but again, this is nowhere near what it should be, because again, I don't have the info on everything. So now this is, I plugged in 2.5% for R, and 12 for both of ends, because the paid payments are monthly payments. So now we have 20K times 1 plus 0.025 divided by 12, and everything raised to 60. So as you can see, the number we are getting now, it's very close, 22,660 cents. So clearly the other one is what, $3 more? The other one is $3 more, but that one is also the upper limit. So it's good enough to use the continuous compounding to make these decisions. Now, again, this is any type of a loan for your credit, or if you want to buy a new computer on a credit card, you want to buy whatever, you can actually figure out how much it actually costs, because you're going to have the price of what you're buying plus the 7% tax, and then if there are any other I don't know, shipping or whatever, and then you have when you have all of that factored out, then you say, okay, my credit card charges, you take a look at the API divided by 12, right? That would be the percent per month. You can run the same calculation. You see the monthly payment for whatever you want to buy. Now, depending on which credit card you have, right, if you have good credit score, your interest, right, will be low, and then divided by 12, if you have bad credit score, they will be high. And that's technically what it is. And again, why is it hard? The money on the credit card is not your money. It's bank's money, right? You are welcome to borrow it because you're the card holder. They are telling you, okay, it's fine to use our money, but you have to keep paying us back. And if you are using my credit card money, you have to pay the interest on it. So you are borrowing the money from the bank. Every time you swipe the credit card, you borrow the money from the bank, and then there is the interest surcharge on that swipe.
When did you see the gold in the treasury before all that?
There is no more gold. That's been not around for a very long time now.
There's supposed to be gold in the treasury, though.
No.
Most banks have like 10% of what they actually have.
Not even, but yeah, they're supposed to. But no. So that's the money talk. And now let's take a look at the decay problems. One of the problems that I had in the past years was for people from the environmental concerns. I ask students to go and research the half-life of a plastic bag and figure out how long will it take to decompose and all of these kind of things. So that's one. Another one would be that marker, right? Because this marker, you see the red one has no cap, it's probably dried out and not useful anymore. That goes to garbage. Garbage goes to landfill, and landfill is going to just be covered with a topsoil, and then people are going to build developments on top of it and then wonder why people with 6 heads and whatever are born. So the half-life of plastic, right? How long will it take for that plastic to decay? It's one of the project problems that you might want to enjoy as you work on these things. So there's a whole host of environmental issues, especially with garbage decay and then also radioactive decay. You might be familiar with a few years back with what happened in Japan. There are a few nuclear disasters in the United States. Obviously, the most famous one in Chernobyl in Ukraine, which pretty much felt in the entire Europe. I wasn't allowed to eat salad and spinach for number of months, actually, because the radioactive cloud traveled from the east towards Europe. So all of these, right, those are environmental issues, right? Also after the nuclear, right, strikes in Japan and all of that kind of stuff. So there is radiation, right, and then we are talking about radioactive decay. So radioactive decay, garbage decay, whatever you're talking about, you have to talk about the half-life first. So decay problems, we first talk about half-life. So half-life, lambda, is the time it takes for an object or a person or whatever to decay half of its mass. Now, what does it mean, this? Well, half-life has a hyphen over here. So you might be familiar with Einstein's equation E equals mc squared, which shows, people say it's conversion between energy and mass. It's not a conversion between energy and mass. It's an equation that shows that energy and mass are one and the same thing. They're just two different sides of the same coin. And the matter and energy freely change form one into another. Now, we don't detect that on this large scale, but on a small scale, you constantly have whole bundles of energy become particle and antiparticle, and then if they collide, they annihilate back into the pure energy. That has been demonstrated time and time again. So we know now that energy and mass is one and the same thing, and the equation that works well to see the, well, you can say a conversion factor, right? How much energy you get from mass, you get to do the conversion E equals mc squared. Now, why are the nuclear bombs so powerful? And they just take a little tiny speck of whatever it is inside. It's because small portions of mass create huge amounts of energy, right? So now, when you're looking at the half-life, everything decays at all times, right? There are different types of radiation, alpha, beta, gamma. I don't want to go into the details of the physics of that, but the thing is that everything decays. Right now, you're sitting here, you are decaying. You are decaying, and those desks are decaying, and the walls are decaying. Everything is decaying all the time. It's just that the half-life for these things are really large, so you are not dying because you decayed, all right? And if you are buried, you are not, right, you just get eaten, right? That's pretty much what it is. So the half-life is the time Half-life is the time in which an object loses half of its mass. So now, if you are thinking about garbage, or so you throw a plastic thing in the garbage, right? Whether it's a bottle or whatever it is, if you know the half-life of the plastic that it's made out of, you will be able to tell how long will it take. But you don't have to actually think about these kind of things too much, because exponential decay graph should be enough of the indicator of when something is going to decay. And the answer is never, right? The answer is never, because the accompanying graph for this is going to be, you have some mass over here, initial mass m, and then you let the time go forever. Well, I don't care what happens there. This line will never touch and never cross the x-axis, right? So it is always going down. It's always decreasing. It's always decreasing and getting closer and closer and closer and closer without actually ever crossing. So what we know is that we have that the plastic actually marker or plastic bag will actually never decay, right? Well, unfortunately, no, that's not true, because the realm for us is quantized, right? And if the realm is quantized, that means that you have particles, and those particles eventually will run out. So you actually can compute when the matter decays, because the particles are just going to be gone, right? So if hopefully you are aware that that plastic marker is made out of atoms, right? And then you can, you know the Avogadro's number, right? And the Avogadro's number tells you how many atoms you have in 1 mole of matter. And then you can, from there, figure out the decay rate, and actually you can figure out when it would decay completely. Now let's talk about radioactive decay. Let's do an example which will have all of this. So now let's talk about, let's say, well, just decay. Tooth whitening, anyone? By show of hands? Tooth whitening. You're using the tooth whitening paste, so you're beautiful.
With teeth,
yeah.
Strips.
The strips, right?
When I had braces, I got the stained teeth that like around.
Right where the braces. I had the same thing.
Yeah. So I'm taking the thing.
So if you were around, 80 years ago, this would be the thing for you, right? Where is it? Right there. So the first ever toothpaste that came out for teeth whitening,
Did nothing. Oh, right.
the first ever toothpaste that came out was called Doormat. Doormat was designed in 1940s, and it was the first tooth whitening toothpaste that was ever made. Yes?
My dad grew up in Huntington County, right? Like right down the street from the guy that works for Colgate.
Uh-huh.
Like all the research and development for toothpaste. He said one of the most interesting things was that like one of the like proprietary smells that they have is actually a derivative of like chicken shit.
The derivative.
All right, so that, yeah, it's, well, no, he has a tab running. Anyway, so, well, hold on. That's not where I was going with this, but I would take that one anytime, actually, because
Yeah, that's not
A chicken.
I was about to answer, but then let's not.
It's just the swell. So the integral.
Guys, focus. So, what is the toothpaste? Here it is, Doormat. So this is the Doormat. You can see the actual tube over here, and yes, it says radioactive on it. So basically, radioactive elements at that point in time were about around 20, 30 years around. The first ever tooth whitening toothpaste contained thorium-229, which is a radioactive element which actually killed everyone who used this paste. So you can see all of the commercials and good things about tooth whitening and then teeth whitening. And then look at this one over here, right? And then once the people figure out how bad it is and all of a sudden, then they see that's another commercial right there, right? But then you have these kind of flyers and things that went out later that were warning people that this toothpaste actually kills. So radioactive elements, right, are not that good for us. So where we start now is, let's take a look at this Doramad toothpaste. So Doramad used radioactive isotope of thorium-229, which has the half-life lambda, if I remember, as 7340 years. I think I should verify that. Doramad half-life. No, Doramad thorium. Is it correct? Thank you. So 7,340 years. Now, what do I want to know? I want to know if there are, so these people that use this, they all died in 40s, right? So they lived few years after so this is the thing of like mid 40s. So by the year of 1950, everyone who brushed their teeth with this Doramad died. So I want to know what is the amount of Doramad that is still around, right? The amount of thorium that is still around, because these people died and then they were buried, right? And the deposits of thorium are still on their teeth. So I want to know what percent of original dose of thorium that is applied to the teeth is still there after what do we have? 70 years has passed since, right? 70 years has passed. So we know that the time frame over here is 70 years, and I want to know the percent of thorium left at their teeth. All right, so we are going to start with the equation that mass at any time t is equal to initial mass m e to the RT. I could put negative R, but you'll see that calculation is going to give us negative numbers, so don't care, right? Now, half-life, we know that the half-life is time in which mass gets cut in half. This half-life here is going to actually calculate R. Now, let's see the way that goes. We know that the mass will be, original mass will be cut in half if you put lambda in. So when we plug values in, this is what you get. From there you can cancel the m's, so it doesn't matter how much you apply actually, right, for the percent that is decay. And we have that 1/2 is equal to e to the, and now we have the lambda, that's 7340 r. You ln both sides on this one, and you have that ln of 1/2 is equal to 7340 r. And then you can calculate this value actually as ln of 0.5 divided by 7340 to give you negative 0.0009443. So that was supposed to be R. R equals, there you go, much better. R equals this number. All right, so now I have R, which gives me the model which says that mass at any time is initial mass times e to the negative 0.0009443t. So this is the model for Doramat. Well, I mean thorium. Thorium-229, which was used in Doramat, so yeah, for Doramat. Now, I want to know what percent of original mass is left, right? So what percent of original mass is left? Well, let's call that percent little percent p times the original amount m e to the negative 0.0009443 t. These m's are going to die. Always. And we're going to ln then both sides. I forgot to plug in 70 over here. Because we are, oh, I don't need ln. Hold on. I need ln because I'm plugging in 70 over here. I'm plugging in 70 because I want to know the percent after 70 years. Percent left after 70 years. There we go. So now percentage is equal to, we just plug this in the calculator. We have e raised to the, and I'll go open parenthesis, second answer, times 70, close parenthesis, to get 0.993. So the percent is 99.3%. In 70 years, all it decayed from that initial thorium deposits is 0.7%. That's how much of the thorium deposits is gone, leaving 99.3% still there. So these are the most beautiful corpses out there. I mean skeletons, right? They have the widest teeth.
Looks like Marie Curie's cells are still too irradiated to study.
Yeah.
Like way too irradiated.
Same like places that, you know, for the nuclear disasters. This is why nuclear fusion is so much needed. Because nuclear fission that we are using right now, we have the you know, you choose between two evils. Do you want coal, or you want, you know, to burn coal, or you want to do the nuclear fission? Like, you don't know which one is worse. Right. They are both equally bad, and even if you don't have nuclear disasters, which we got pretty good at it, so we don't have the, I mean, yeah, there was one just, you know, a few years back in Japan, but we got pretty good at it, right, in terms of safety and all that kind of stuff. But the problem is nuclear waste, you know, and you can't really fire it into space because everything that goes to space is cost per pound, thousands of dollars. So you can't fire it up in space. Plus, you are creating a lot of space junk. We do already have a lot of space junk. Now you have to fire, you know, radioactive stuff. So all we do is we just bury it in the mountain, right? That's what's happening with the nuclear waste, because we don't have anywhere. And you see how long it takes. I mean, after 70 years, only 0.7% of that decayed for this. So that's pretty much, you know, it's bad. So these half-life problems now can be used to do carbon dating. You can use them to figure out garbage decay, and they're all the same way. As long as you know the half-life, I don't care whether it's radioactive element or plastic, right? You can use the procedure to figure out the R, and once you know R, from there you have an exponential model and you can do whatever you want. Now, again, you can take the derivative of exponential model and to see how much stuff you are losing per year, or how much stuff you're losing per 10 years or whatever. You can do those kind of calculations. But for now, I mean, you know, the most important part is for you to figure out which way is to calculate that R. Once you have R, you have exponential model, and after that everything is easy. We are going to upgrade this problem once more in chapter 7, and then you will have to wait all the way to differential equations to do even more with these types of a problem. The last problem that I want to do is also a decay problem, but it's a very important decay problem, which is metabolizing drugs in your system, right? So anytime you take any kind of a pill, right? That pill will actually have its half-life to metabolize in a system. So if you go to if you install Mathematica, or if you go to Wolfram Alpha, you can type in any drug. So let's go with Advil, for instance. And if you go and type in any drug, they give you the chemical composition and all of the other stuff that is related to that drug. And see the structures and so on. You can cook this up on your own.
So Advil is ibuprofen?
Yes.
But ibuprofen is ibuprofen.
And Advil too. And then if you take a look over here, it says biological half-life is 1.9 hours, right? So now when I call that 2 hours, right? That means that half of the dose that you take, let's say 200 milligrams, right? Half of the dose in 2 hours will be gone. So you're left with, let's say, 100. And then after another 2 hours, you are left with 50. And another 2 hours, you're left with 25. And another 2 hours, you're left, right? But see, the trick is that after 4 hours, you pop another dose, right? So if you are following the pattern, every time you take a medication drug, you are actually increasing the dose. So it's not that the previous one wore off. Remember the exponential decay? Yeah, you still have everything you ever took since the day of your birth. You still have it in your system.
Yeah, I'm a drug addict.
So if you're starting with 200, you wait 2 hours, you have 100. You wait 2 hours, you have 50. But what happened after 4 hours? You took another dose, so you were at 250. Then you wait 2 hours, it goes down to 125. You wait another 2 hours, that goes down to, what's that, 62.5.
Yep.
And then 4 hours is up, what? You pop another, right, thing, and then now you are at 262. Do you see what's happening? Every time, so you started with, let's say if you never took, ever, right? Before, you start at 200. The next time you take, it's at 250 actually, the level. And then the next time you take it, it's at 262. The decay is not going, right, the half-life is cutting it in half, and cutting in half it's cutting the remaining amount in half. It's not going to be, first 2 hours is 100, and the next 2 hours is 100, and it's gone, and you're ready for the, right? So, people get addicted, right? Of course, right? It's very easy to understand a lot of things in life and explain a lot of things if you understand basic rudimentary mathematics, which is what this class is.
This is basic math.
Elementary mathematics through differential equations. First non-elementary math class is linear algebra.
You probably took this at elementary school.
It's okay. You just hang in there.
Don't worry, I don't get offended. I don't want to know what.
So now, no matter which drug you pick, right? You type that in, gives you biological half-life, and you go and figure out from there. So that's another, cool thing to look into in a project and so on. So and you can also see that overdose is very easy if you are taking the pill before prescribed. Even if you are taking it at the prescribed intervals, the levels are constantly, every time when I draw the lines when you take a new step, right? So anytime you take the new pill when it's prescribed, the levels are going up. Now imagine if you pop another one over here, then it's 300. You cut that in half, it's 150 plus 200 is 350, right? You see that in that case, the levels will be even higher, right? And we know from exponential decay, it never goes away. Well, eventually it will, but you can actually, again, figure out from a single dose, right? Figuring out You know its mass. You can figure out, you have the equations over here. Now that's more for a chemistry geeks in this classroom, and bio geeks obviously. Go and figure out, you have the composition, right? So from the composition over here, you can figure out all of the masses you want and stuff, and figure out how many atoms you have. It's going to be huge. And then take a look at the decay model. See when everything is going to be gone, right? Everything. And it's not lifetimes, spoilers. So these are the things that you can do for fun on a side. So medication. Look at bio half-life. Calculations are the same as for radioactive or garbage, same stuff. I mean, our medical field didn't really progress at all, because now instead of calling them magic potions, we call it medications, and instead of calling them shamans and whatever, now they're called doctors. It's the same deal. We just updated the wording on it. All right. So we have, look at the bio half-life, and I'll just say Advil over here. 1.9 hours. So lambda, right? Lambda is 1.9 hours. And that's that. That's 6.9. Let's go hit the break. After the break, we have the last section of chapter 6. Or maybe, wait, hold on. It's 6. So yeah, no, we're going to push that one for tomorrow. So no more new material today. The rest of the class is lab time. Yeah, so we'll continue tomorrow. So if you haven't done the class prep 610, it's due tomorrow. If you already did it, it's fine, it's done.